Okay, welcome to JC Connect. In the previous class, we were discussing about the fire demand. So, and we have left with one um, small problem: how to calculate the fire demand if the number of jets as well as if the number of fire breaks has happened in a year. So, so this fire demand is required for firefighting. Um, for example, if any fire break is going to happen, how much water is required for the to stop the fire? So, in thickly um, populated and industrial areas, normally the fires breakout is going to happen, and it may lead to serious damages if it is not controlled effectively. So, the main um, objective of this fire demand is to satisfy the um, or to control the fire at the uh, point where it is going to catch. Suppose if it is going to catch at the 20th storage of the building, it should be able to reach at that point. Means a lot of difference is there. For example, you have a first storage building. Assume that it is first storage building. Then you have the long building if it is there. If it is of 20 floors, so then the jet, the very important thing is that here one jet will be there. Jet has to reach even for the 20 floor 20 floor building. Then that much pressure has to be maintained. Pressure has to be maintained. Then how much it should be maintained? That is very important. So uh, the pressure, it should be 100 to 150 kilonewton per meter square. That is very important. So even if it is 20th floor, if you are maintaining this much pressure, definitely it is going to reach at that point. Then if that much pressure, even sufficient quantity also it is required. So one is pressure and one more is quantity. Pressure and quantity both are very important. Sometimes pressure will be there, sometimes uh, that flow. Normally the quantity or the flow, it is um, given by liters per day, or it is given by meter cube per second or meter cube per minute. So these are the units of flow. So very important, flow. The unit of flow is, remember, flow unit is either it is liter per day. This you can convert it into meter cube per day, or you can convert this into meter cube per minute, or you can convert this into meter cube per second, or you can convert this into uh, liter per minute, or you can convert that into liter per second. So pressure is totally different from the flow. Both are different. So whenever we are talking about the fire demand, so two, that is pressure and quantity, should be maintained properly. So if I say it is a pressure, so 100 to 150 kilonewton per meter square, that had to be maintained. Then how much flow should be maintained? So this one, 1100 liters per minute of flow should be, means per minute it has to discharge. This flow or discharge, both are same. Flow or discharge, both are same. Sometimes I'll use the word flow, or sometimes I'll use the word discharge. Both are same. So if I say it is 1100 liters per minute of uh, flow should be maintained to reach at the 20th floor building. Hence, in a big city having a population of 50 lakhs, suppose in that city, if six fire breakouts has happened in a day, assume that you have um, uh, one house is there, second house is there, third house is there, fourth house is there, fifth house is there, sixth. In all six our house are going to catch a fire in a day, assuming with a 50 lakhs population. Assuming that you have 100 houses in a city, then in that 100 houses, if six houses are going to catch the fire, then in all these six houses, normally I already said that in each street we have hydrants will be there, means standports. So they are going to, if any planned city will be there, in each of the street, they will keep the hydrants. So this hydrants, assume that they are using the three hydrants. So one, two, three hydrants. If they are using it, means these are the stand near the stand posts. They are going to keep these all three hydrants. From that hydrants, they are taking the water to stop the fire for all six houses. Then suppose these hydrants are operating for 3 hours. Means if you want to stop the fire, if you want to stop the fire, uh, they are using all three hydrants for 3 hours. Means all three hydrants are running for 3 hours. So then we have, so then how much quantity of water is required to stop all these six houses fires? Then how this can be calculated? How exactly? The first one, we already recorded how many fires are happening. So number of fires are six, means six houses. Six houses are catched the fire. Then, so how many hydrants they are using? Hydrants, hydrants. That is three in each of the um, street. They are having three hydrants. So then, how much discharge it is making? So it is 1102 liter per minute. Here the units are very important. So this 6 is related to the number of houses catching fire. This 3 is related to the number of hydrants, and this is related to the liter per minute, very important. Then how many hours it is taking to stop that fire? So it is means that hydrants are running for how many hours? So this is for 3 hours, and this they are converting into minutes. So 1 hour is equal to 60 minutes. So then, if I want to calculate the total quantity of water is required to stop fire for six houses, that is equal to number of fires into number of hydrants into flow or discharge in a liter per minute, then multiply by 3 hours of hydrant has to run, then conversion into minute. So then what will happen is that if I do that calculation, oral calculation, then it is equal to 6 into 3 into 1100 liter 1100 liter per minute, then it is multiplied by 3 hours, that we are converting into 60 minutes. Then minutes get cancelled here. The remaining, it will be, if you multiply all these calculations, you will get 356,400 liters. But this is happening per day. In one day it has happened, so I am writing as a per day here. So total, if you see the flow, how much quantity of water is required, that is equal to, this is 356,400 liters per day. Then if you want to calculate how much uh, per person, if you want to calculate it, whatever the total liters per day is there, so divided by 50 lakhs. So why I am dividing it by 50 lakhs here? Very important. In this problem, is said that, so 50 lakhs population is there for a city. Then if you do that, so you will get less than 1 liter per person per day, if they ask how much it is required. Sometimes they may ask the problem in this way also. Sometimes they will ask the problem in the other way also. So should be very careful while analyzing the problems. So now we'll move on to the uh, some of the empirical formulas which are required to calculate the fire demand. Sometimes if the problem is asked in that way, you can calculate it. Sometimes um, if they are not asked, if they use us to calculate the empirical formulas, then we have to use the some of the standard formulas for the calculation of the fire demand. So why this uh, formulas have developed? The only reason behind that, if you see the previous calculations based on the LPCD, for example, based on the population, if we are calculating, we are getting 1 liters per person per day. Sometimes it may not be correct. And uh, to avoid this kind of problems, or whether it's a zero point 0.5 liters or zero point 0.6 liters per day, so they have continuously studied and they have conducted some of the research how the fire demand can be calculated, not based on the per capita demand. So they did for some based on the population, total population. They calculated some of the empirical formulas. Of course, these empirical formulas are not exactly correct, but in some instance, you can use all those formulas. You can use all those formulas to calculate the fire demand. So the first fire demand, that is the Kuchling formula to calculate the fire demand. So this is given by the Q is equal to this is given by Q is equal to 3182 to the root of P. So very important here it is that, so Q is equal to 3182 root of P, where P always it is in thousands. Remember, thousands means, for example, you have 10,000 is there. You have population is of assume that it is 10,000. Then I have to substitute the value as 10 in place of P here, not 10,000. Then Q always it is in liters per minute. Remember, always these are the empirical formulas. They have developed it by conducting successive experiments. So how they have arrived to this formulas? So they have collected some of the cities population, some of the cities population, around 100 samples, 100 cities population, and they have calculated how many fire breaks are going to happen in these 100 cities. Then this Kuchling scientist has calculated based on some of the assumptions, like okay, 5 fire breaks are going to happen in each cities. Then they have calculated it and they have arrived this empirical formulas. So Q always it will be in liter per minute. P always it will be in thousands. Then this is a constant. They have arrived with the successive experiments. So then Freeman's formula. So here it is also Freeman's. It is Q is equal to 1136 P. This has to be completed. So 1136 P divided by 10 plus 10, where Q and P have the same meaning as in the equation. So here also Q, it is in liters per minute. So then P it is in thousands. Then the National Board for Fire Undance writer's formula. So according to this, his recommendations, actually this is National Board of Fire under writer fire. Actually, National Board of Fire. It will be there in US right now, and it will come under the American Insurance Association. This can be calculated with the help of this formula, where Q is equal to 4637 root of P 1 minus 0.01 root of P. Here also it is same meaning. P it is in thousands and Q it is in liters per minute. So one very important questions normally in your examination it is going to ask, calculate the fire demand fire demand using the empirical formulas. So you have to use all these formulas. So whatever this formula, this formula is heavily congested city. You have to use this formula only when it is central congested city. Suppose if it is a residential type of, if it is distributed for small or low buildings, you can use directly this value. No need to calculate the formula. You can use directly 2200 liters per minute as required. That is Q. If it is a larger or higher building, so then you have to use 4500 liters per minute. So then if it is apartments or tenements, so you can use this value directly. Then if it is uh, high density with build-up sections, if it is a high dense, like you have a lot of colonies with high density populations, then you can use directly this values. So these are the values they have arrived by considering uh, uh, different types of cities. They have calculated with some of the samples, like sometimes assume that for the first how they have arrived this value, but they have calculated 100 samples of small and low buildings, then they have arrived this value. They have again considered 100 samples samples of larger and higher buildings, they have arrived this value. Then high value residences, they arrived it, then they arrived this value. So like that, they have calculated the samples and they have arrived these values. If they ask directly, you can take all these values. Sometimes if they ask to use the American Insurance Association formula or the National Board of Fire by US, then you have to use this formula only directly. That is this one. No need to go for the remaining values. So then population forecasting, um, we will discuss in the next class. What we'll do, we have around 8 methods are there to forecast the population. First one, that is arithmetic increase method. Then that is geometrical increase method. So what we'll do is that in each of the classes we'll try to cover one or two methods. If all 8 population forecasting methods are over, then this module is going to over. So maybe we'll try to spend 4 to 5 hours of class for this population forecasting. So what we'll do is that each population forecast method will study, and we'll take one or two problems from that.